the third part of lecture 5. We are going to talk about some of the applications of polymer matrix composites. The first one is what we are finding is that there are more and more um, components, especially um, the primary primary type of components are being built with composites. Previously, they only used to be used for secondary type of components, but now there are more and more primary stage components being built with composites. For example, here in the new Gen X engine made by GE, the carbon fiber epoxy composites are being used for actually making the blades, which have such very small tolerances, extremely small tolerances, maybe like less than a millimeter and things like that. Um, this is another view of the Gen X engine. Um, the the most important one recently is the fuselage of the Dreamliner. Now, I don't know if you have read anything about it, but the main difference is that the especially the windows are much larger. In the older uh, planes, which were made from metal fuselages, they were, because it is a portion of structural weakness. These window areas are not that large, but because these composite materials are much stronger, you can make these windows to be much larger. So what this does is it lets in more light in the composite. And interestingly, the one of the companies making these um window frames especially, is right here in Oklahoma at Nordam. So that gets fitted exactly over the whole areas. And this one is made, the fuselage is made by a combination of fiber placement and filament winding. The other important application of polymer made composites is windmills. And what is interesting about windmills is that they are one of the largest users of polymer made composites. And it's made in half. When you look at the turbine blade, they are made in half and just bonded together. In the windmill, as you may not know this, it converts the kinetic energy of the wind into electrical energy with the power. So it is directly proportional to the area of the rotor plane. And so the longer the blade, the higher the area. So for a given wind velocity, if you increase the radius of the windmill, you can increase the power of the windmill, which directly reflects in the amount of electricity that can be generated by the windmill. So in the 1990s, when they started being built, they commonly had about 15-meter long blades and could produce 50 kilowatts of power. Now they are being made from 60 meters, so 4 times that. I mean, in 2008, so it could produce 5 megawatts of power. And now what you will find is that there are windmill blades being built that are 100 meters long. So you can imagine the amount of power that can be generated by these windmills, wind turbines. So In this case, in this picture, each rotor blade is 36.8 meters long, and this is probably a windmill farm in Europe. There are also a lot of windmill farms being built on the, if you have driven on I-35 along the Oklahoma-Kansas border, you will find that on the Kansas side, there are many wind farms, I mean windmills being built as well as operating. So how does all this reflect in the way composites are used? The It reflects in the way the value of the constituents goes down as it goes towards the waste, or this is the ideal format. So the polymers and the fibers have the highest value, but after the product is made, the when it is going towards waste, it should not have, it should probably have only a portion of the value of the polymers and fibers and matrix um, in the left in the pot. Now let's look at um, the another type of composites called metal matrix composites. Metal matrix composites are pretty much similar to casting, and they are, or casting or forging. And because the way the composite is made is pretty much similar, but the ingredients are slightly different because now you have the fibers as well as matrix to put together, and you can use different forms of manufacturing. Like you can use a powder process where you take the matrix in powder form, the metal in the matrix powder form, and the fibers, chopped fibers mainly. Or you could have continuous fibers and you apply the powder in between them, and you process them together to make the final part. Or if you are making a casting process where you take the composite and you melt it and you cast it into different forms. So you can do pressureless casting or pressure casting. You can also have specialty processes like spray forming, roll bonding, explosive bonding, etc. And once the part is made or once the billet is made, then you can use the rod process such as extrusion, rolling, forging, etc., which is very similar to what you use for metals. So there is also another form called squeeze casting. So you cast it into a preform of fibers, uh, the metal in molten form. So it creates the final shape. So the liquid metal or casting route is where you are taking the particles of the fibers, you stir them into the molten alloy, and then you can cast it into a mold, or you can take it and forge it into the final shape. So there is a little bit more further processing required for that. And you may also need to work on the particles or the fibers so that the fibers don't get degraded by the molten metal, because the molten metal can be extremely corrosive and it can reduce the properties. So if you want the right kind of composite properties, you want to make sure that they are not going to be degraded. And in this case, the fibers most of the time they are chopped form, and there is a maximum fiber volume fraction or the particle fraction, which is about 15 to 20%, because otherwise you are going to end up with a lot of porosity. And if you have a binder in the preform such as a silica, it can react with the molten alloy and alter the composition. So you have to make sure that these things don't happen. Okay. So this is in the conventional casting, you can put it together and cast it like in the foundry, or in this case you take the ceramic particles and you take the aluminum. So in this case, this would be the example for an aluminum alumina metal matrix composite. Or if you are doing it by the standard method, I mean non-standard method, such as you melt the metal in an electric arc furnace, and then you add the particles, and then you have a mortar, and you mix the two together so that the particles don't settle down during the processing itself. And then once the metal is molten, you can pour it into the mold. So one of the issues with metal mixed composites, especially with when you are using particles and things like that, is those particles can have a density that is higher than that of the molten metal. So those particles can easily settle down. And the sedimentation is actually a greater problem at low volume fraction. And at higher particle content, the particles will interact with each other and hinder the sedimentation. The next one I mentioned a little bit earlier, it is called selective squeeze casting or pressure casting. In this case, you can get a near net shape, and this is one of the ways in which metal plates for uh, ballistic protection are made. For example, you take carbon fibers and you cast it. I mean, you cast aluminum metal around it, or other types of metals around it, and you get extremely good toughness as well as strength for these materials. And then once the part is made, you can also squeeze it so that you get a final shape that, or you put it into a mold and you take a carver press or pressure platens, and then you apply a pressure to get the final shape. So most of the time the final shape is a um, rectangular or a square block of material, which is the squeeze cast part. You can also do powder processing of these materials. So you take small particles and then you blend it together. You do what is called cold isostatic compaction. Then you hot press it into a shape, and then you extrude that into the final shape so that you can get the fibers aligned in the direction of the extrusion. So you get reinforcement, selective reinforcement in specific directions that you require. You can also do what is called the foil fiber foil method. You lay it up and then you uh, put it together and you get the final shape. So this is a method that is used for materials like superconducting materials. So that is so you take the powders itself and then you make it into a fiber, and then you stack up the fiber and then you extrude that into the final shape. Another technique is for making uh, titanium composites with silicon carbide reinforcement. So you take those fibers and you infuse the preform with titanium alloys, and the titanium alloy will react with the silicon carbide fibers around the surface and form extremely good bonding between the matrix and the fibers. This is another example of that. Um, and many times you want these materials to have eutectic composition, because that way you can have a lower melting point, because some of these fibers have specific temperature limitations. So you would only use a eutectic type of alloy to use as the metal matrix itself. You can also use what is called a monotectic alloy. So there are specific examples, but I just wanted to give you an example of some of these types of materials. Like in this case, this is tantalum carbide fibers and a nickel alloy matrix, um, and things like that. Anyway, that's the third part of the lecture 5, and I will continue after this lecture and another section.